Hey there, everybody. I'm Chris. I'm a research scientist at the University of Illinois. My background is in geodynamics, upper mantle geophysics, but more recently I've been doing some work with YT and extending it outside of the astrophysics domain into other more geoscience-oriented domains. So today I'm going to tell you about ytxray. So let's start off with a little intro. So xarray, you all know, the labeled and chunked array manipulator that we all know and love. Don't really need much of an intro with this audience. YT is a 2D, 3D visualization and analysis tool to work with volumetric data. It was initially designed to work with astrophysics simulation data on AMR octree meshes, and has since been extended to cover other grid types, other particle-based codes, and it works in a chunked way so that you aren't loading all of your simulation data into memory at once. And so you can do a variety of things. So you can create spatial plots, slices, projections. You can do 3D volume rendering. You can make statistical plots like 1D, 2D binned statistic plots. You can also define fields on the fly using functions so that you can actually pass in Python functions that get called when you need a field, so that fields are calculated on the fly as you need them per chunk. And so what I've been working on is simplifying the access to YT for xarray users. And a lot of this work actually comes out of like my own research, because I use both xarray and YT together. So typically what I do is, in my workflow, I'll use xarray for any initial inspection, any analysis on arrays that I need, and then I'll pop that data over to YT to make my final publication quality figures. And so I often find myself making figures like this. This is just a slice plot through a 3D seismic model of the upper mantle in the western US. So the plot was made with YT. YT has an optional card-to-py dependency that helps you make maps and switch projections and stuff. And to give you an idea of what this involves, here's some pseudocode that kind of lays it out. So you start off by just opening your xarray data set. As normal, there's some process in which you extract your arrays. You need to know something about the bounds of your arrays. And then you pass that off to YT to load in this case, as a uniform grid. And then that YT data set you can use in any, this is just a standard YT data set. You can use it in any YT operation. A more complex example is this 3D volume rendering. So this is, again, another seismic model of the upper mantle. In this case, different model, but still in the western US, that shows seismic anomalies beneath the western US, where the blue colors are seismically fast, the reds are seismically slow, and you can kind of spin it around and look at correlations with surface tectonic features. And again, to make this plot, you have to first open up the data set in xarray, get the actual data arrays that you want, get the bounds, and in this case, so YT's volume rendering is limited to Cartesian coordinate systems, and so there's this extra interpolation step that I have to do to take the data from the geodetic coordinates over to a Cartesian coordinate before loading it into YT and doing the actual volume rendering. So these two steps are pretty painful generally. So in the first case, usually what you end up doing is making copies of arrays in memory, which is not ideal. And then in this 3D volume rendering case, this interpolation to Cartesian is a pretty expensive step, and ideally we wouldn't have to do these things. So with that, that's where ytxray comes from. So ytxray is an xarray accessor object. It's built to streamline the data transfer from xarray to YT. Ideally, we're going to avoid copying data. We're going to support chunk data fully, and then we'll talk more about this later, but it allows you to do some dynamic interpolation by chunk in order to facilitate some of the YT operations. So with that, the initial, pretty early stages here. So there's not too much involved with the package at present in terms of the actual API. So after you import ytxray, it comes with the open dataset wrapper of the standard xarray open dataset, and all this does is check some extra directories that YT normally checks, where I tend to store all of my data. So I just added this wrapper for mostly my convenience. But if you happen to use YT already and use these directories, it's pretty nice to be able to check those directories for your data files. So, but after that, so this DS here is just a standard xarray data set. And after you have imported ytxray, you get this accessor attribute, ds.yt, from which you can call load grid and get back your fully fledged YT data set that you can use anywhere in YT. So to kind of show you this in action, here's another example from upper mantle geophysics. So this is opening up in this case, this is a global seismic model. And so you open it up with the open data set as normal, just call this load grid, get back the YT data set, can use that anywhere in YT. And in this particular case, this is in YT terminology, a phase plot here is a 2D bin statistic histogram sort of plot where you pick an x-axis, y-axis variable, and then for each of the bins you can do things like count occurrences of variables. In this case, I'm finding the mean value of this melt fraction number across the whole model domain. And so this is a really nice way to, for me, look at trends that tell you something about the mineral physics of the upper mantle and how seismic waves respond to the material properties. So in the ideal case, if everything works out, this process will actually set up dynamic references to your open xarray data set, so it won't actually copy any arrays. It'll only read in data as needed by YT. And in an ideal case, you'll also have access to all the fields that you have in your normal xarray data set. But things don't always go to plan. So there's a number of complications between sort of like the kind of compatibility complications between YT and xarray. So the first condition is that all of the fields that you load into YT pretty much have to have the same dimensionality. So like if you have a mix of 2D, 3D variables in your xarray data set, you have to provide a subset of the fields you want to load into YT. The fields have to have spatial dimensions only, so Cartesian or geographic data, but no time dimensions. So if you have time dimensions in your fields, you got to pick a time step that you want to load into YT. And then the final complication that is a little annoying that I'm hoping to fix somewhat soon is that YT has fixed names for the coordinate axes. So like X, Y, Z, latitude, longitude, altitude, whereas in X-ray, it's more general. Your fields can have any dimensionality names. The names don't, unless you're using CF conventions for certain things, you can use whatever names you want for your arrays. And so to get around this first set of complications, there's a number of things in ytxray. So there's a known coordinate alias dictionary where you can add the name of the coordinate axis in your native arrays and just map it to an axis name that YT understands. So you can just do that for any array names that you have. And then if you need to provide subsets of fields, you can just use this fields parameter, give it in this case, precipitation temperature fields, and then you can pass in selection dictionaries as you use an xarray in order to subselect time steps. So that gets around those complications. The next set of complications is a little trickier. So right now, ytxray supports two types of grids. So the first is a uniform grid. Pretty simple. You have some delta x, delta y, not shown delta z, but these are constants. They don't have to be equal to each other, but they are fixed along each axis. And then we also have our stretched grids, where the grid spacing in each dimension can vary along that axis independently of the other axes. And most data that you load up into xarray, you have your data points defined on the nodes of these grids, where you have, so the shape of your data array matches the shape of your coordinate arrays. So this presents a little bit of difficulty in YT, because in YT the grids typically expect face or cell-centered values. So in the case of a uniform grid, this isn't too much of a problem, because we can just wrap a new grid around our existing nodes, and then they're now cell-centered rather than nodal values. Stretch grids are a little bit trickier, and right now when you load these into yt from xarray, it'll actually interpolate to cell-centered values. So not necessarily ideal, something that we will be working on. And the final complication as to whether or not you actually get dynamic references to the chunked arrays as opposed to loading everything into memory really deals with the internals of how yt handles chunking, which is fairly different from xarray, I think, and a lot of other kind of array packages. So we're going to talk a bit about yt internals here, which I hope you'll find interesting, because I do. So in yt, the sort of the on-disk or array representation is tied inherently to the spatial geometry of your data set. So each of these chunks might reside as like an index range or in an on-disk file or in memory array, or in separate files on disk. And when you load up that data set into yt goes through this indexing process where it records the spatial extent of all of your chunks. And it does this in a lot of different ways. Won't go into too much more detail about that. But if we think about our kind of simplified uniform grid cell-centered values, this means that yt will wrap grids around ranges of your cell-centered values. And in yt, the process of figuring out how to wrap those, how to actually create all of these grids around your subsets of data occurs in what we call in yt front ends. So these front ends are optimized I/O submodules for specific formats from specific code outputs. So it might be different data file types like HDF or NetCF, whatever they are, but they also might be different grid types. And so usually to load data into yt with the full parallel capabilities, you have to spend a lot of time kind of figuring out how you want to actually load in the different chunks of your data. And you typically have to write a lot of code. But we'll come back to that in a minute because it's not quite as hard anymore. But what this gives you basically is it allows you to subselect data pretty efficiently because yt has a set of geometric selections. So for example, a sphere object that is centered at some center, has some radius, yt will go through and actually discard any of the grid objects that don't intersect that sphere initially. And those are like pretty quick, cheap computations because they're just geometric intersections. So you can avoid loading in data pretty well. And in terms of code, this just kind of looks like this, where you create a sphere object centered at some point with a radius, and then that object you can pull out any field values. And what happens when you do this in yt is yt first goes through and finds a subset of grids that intersect that selector object. And then for each of those grids, it finds the cells that lie within that selector object. And eventually down the line, there's a point where effectively it calls some function that returns the actual field data for these cell points. So it's not until this point that it actually tries to read data from disk or pull in index values from other arrays. And with recent advances in yt, it's actually gotten a lot easier to change just how this function operates. And so in ytxray, what we do is we generate this loading function dynamically so that we can have references to the xarray data set that you've opened. So in practice, this is a much simpler version of what's actually implemented, but you kind of get the gist of what happens. So within this function, it has a reference to your open xarray data set from which you can pull out references to any of your xarray fields. And the grid here is the yt grid. And so from that, you can get the active index ranges of each grid that you need, and then actually just select from your xarray variable. And if that variable is delayed, at this point, we return it to memory so that yt can actually use it. But this is only happening to one chunk at a time. So in ytxray, this load grid function has a chunk sizes argument that sets up the yt grids. This scalar value will just is the number of elements you want in each direction for the grids. You can also give it a tuple here if you want to vary that. And then when you make a slice plot, for example, and annotate the grids, this is just some test data here, but you'll get a figure like this where so these are the actual yt grids, and in this case, Inside these YT grids are a subselection of xarray dask chunks. In this case, I think the ratio is like 4 xarray dask chunks within one YT grid in cross-section. So right now, they're not necessarily mapped one-to-one in terms of the grids, the YT grids to the xarray dask chunks. But that is something that we are working on. So to kind of summarize the grid support we have right now, so if you have uniform grids, you'll be able to use ytxray and YT pretty well without a problem, I think. So if whether the data is in memory or you have chunked arrays in xarray. With the caveat that right now, those dask chunks won't get aligned with the YT grids quite yet. And then if you have stretch grids right now, if you're okay working in memory, it'll work with the caveat that right now it does have to interpolate to the cell centers. So if you're worried about losing that information, you'll have to wait a little bit till we figure that one out. And then there's a couple of upstream changes we need to YT in order to support the multiple stretched grids within a data set. So we're kind of waiting on a bit of work there. Right. Okay, so real quick, one of the, I think, kind of cool things this sets up is the ability to apply interpolation and transformation functions within the YT grids to the xarray data. So this is the previous function we had where you pull out your xarray variable, you select the indices from that variable that you want, you load them into memory. But it's totally possible, and this is actually how the stretch grid interpolation is implemented, to instead pull out the XYZ expected coordinates of the YT grid and hand that off to some function that will interpolate or transform from whatever coordinate system your xarray variable is into the coordinate system that YT needs. So in the case of stretch grids, it's all Cartesian, or it's all the actual coordinate system isn't changing, it's just interpolating. And that's actually implemented with just xarray's reference to the SciPy interp functions. But this means that in this sort of case, coming back to this 3D volume rendering example, we're getting close to our goal of being able to just open our xarray data set, get a YT data set that includes references, and not do any of that interpolation until YT actually needs it on a per chunk basis, so that you don't have to spend all that time pre-computing an interpolated function. And so the YT volume rendering code is parallel and works by chunk. So you can do that interpolation as needed by chunk. And this also opens up the possibility to load in more easily non-coordinate systems that are not necessarily explicitly length dimensions. So if you have hybrid pressure coordinate systems where one axis is a pressure rather than altitude, you could actually put in your function to convert from that pressure to a height within this grid object, so that you don't have to do that beforehand, so that you can load it into ID and do some 3D volume rendering. So I think that's kind of cool. So to summarize, right now you can get back a YT data set pretty easily with load grid. Talked about those caveats already. Let's just go to a few final sort of what's next points. So we're hoping to improve the stretch grid support so that we can actually have the same chunking support for stretch grid as uniform grids. One of the things I would like to do more of is create some more geoscience-oriented examples of using YT and ytxray, because I recognize that a lot of the documentation for YT is still very much astrophysics, and that is definitely a difficulty when you're starting off with using YT. And so I'm hoping that a large part of the ytxray documentation will be just examples to get you used to working with YT. And don't need to go through all of those right now. So yeah, so thanks. Thanks for watching. Thanks to Matt Turk and the YT dev team. If you want to learn more, the developments happening at this repo, we do have a read the docs page. And yeah, feel free to contact me with any questions. Thanks.
All right, we have plenty of time for questions. So let's see some hands. Check the Slack. Going once. Max.
So I know you were talking a lot about the sort of chunking strategy within YT and kind of how it's different from kind of the broader like Dask or even some of the other packages. I guess this is more of a YT general question. Do you think at some point they'll sort of conform to kind of broader standard or broader conventions that are kind of used within the ecosystem?
That's a good question. I've actually done a lot of work trying to use Dask within YT and actually like create some like Dask chunked arrays within YT that can work with the YT grid operations. And it's definitely something that we could do. I'm not sure, you know, after a lot of time working on that, it got to the point where like we couldn't actually see much benefit in terms of like, in terms of speed up for YT. You know, like YT is fairly efficient as it is, as it was built. So I'm not sure how far we're going to go with that development. And I'm also not sure that it's so much needed because like once I am mapping better the actual chunk ranges of the xarray arrays, then all of that is kind of taken care of by xarray. It's just like making sure they line up with the YT idea of what a chunk is. Yeah, thanks.
Hi, I'm curious about the motivation for the API for this library. Like, are you using any functionality? Like, why are you inheriting from xarray rather than just having like a from array in YT or something?
So it's not actually inheriting from xarray. It's like it's a new accessor object. But the reason is that because I do a lot of my analysis in xarray. Like I pull out data, I like send it off to other libraries and stuff. And so when I'm working, I'm often like mostly based in xarray, but then I just want to like make this one figure in YT. And so rather than having it on the YT side to like bring in the xarray, it made more sense to me to like connect it to xarray. And the other part to this that I didn't mention anywhere yet is that one of the things I'm thinking about is exposing a lot of the YT API within the successor object so that you don't have to have this intermediate dataset object to make like a slice plot using YT with your xarray dataset. Yeah, so I guess that's the extent to which I've thought about that.
Any other questions?
Thank you. That was a great talk. Just a quick comment. I left an issue on your repo, but you can use the CF conventions to do that automatic renaming and guessing that you like. And I wrote a little package that encodes those rules. So you could use that and benefit really quickly.
Yeah, great. I will look into that.
Thanks.
Yeah.
All right, any more questions? All right, if not, well, thank you again.
Great. Thank you.